Let's look at one more example to make sure we're comfortable with all of these new ideas in our vector algebra. This example is a little bit long, so I'm going to split it into two videos. So we can see here we have three field quantities, P, Q, and R, each of which are divided into their X, Y, and Z components, except for, of course, P, which we see does not have a Y component. One thing to note about these fields before we move on is that these are what are called constant or uniform fields. Now, the reason these are constant or uniform fields is because there's no spatial dependence. So for instance, if we had something like a y squared term here, now we have a spatial dependence. Or of course we could have an xy here, or some dependence on z as well with any of these terms, and if we have that, our field is no longer uniform. Remember, in general, we can also have dependence on time, so we could have t in any of those terms as well. But in order to keep things simple in this video, we're just going to look at these uniform fields. So again, this example is a bit long, so in this video we're going to look at these first three parts of the problem, and we're going to come back to the latter three in our next video. So let's just go ahead and take this first part down here to our next screen, and let's find the answer to this first part here. So what we're looking for is P plus Q cross with P minus Q. All right, so I'm going to go ahead and, well, so as always, of course, I would encourage you to work these examples by yourself first, so maybe pause the video and give that a try. I'm just going to go ahead and write our values down here. You can be looking at the notes in Canvas or scroll up or go back to a previous point to confirm these are right. But for our P, we had a 2 for our X component, a 0 for our Y component, and a -1 for our Z component. I'm using angle brackets because this is a vector. We're adding to that Q, so for Q we had 2 for our X component, -1 for our Y component, and 2 for our Z component. And we're taking the cross product of that with the difference of the two vectors P and Q. So these are the same two vectors, so 2, 0, -1 for P. Now we're subtracting Q, which is 2, -1, and 2. Okay, so first we're going to do the addition and subtraction. And so again, for our first term, we're going to do this component by component. So we're going to say our X component plus our X component, so 2 plus 2 is going to give us 4. We then move on to our Y component. So now we say 0 plus -1 is going to be -1. Same thing for our Z component. We're going to say -1 plus 2 is going to give us 1. And we get something that looks like that. Now we want to do the same thing for our subtraction. So we're going to find the second vector that we're in our cross product. So again, component by component, 2 minus 2 is going to give us 0. 0 minus a -1 is going to give us 1. And then finally, -1 minus 2 is going to give us a -3. Okay, so now we're ready to do our cross product. So if we want to do the cross product, we can do our definition here. We know we have our unit vector in our X direction, unit vector in our Y direction, unit vector in our Z direction for our first row. And then we're going to put our first vector, 4, -1, 1 in the second row, and then in the third row we have 0, 1, -3. And of course, remember the order of this matters. We can't swap around the second and third row, otherwise we're going to get a negative value, so it swaps the sign of our answer. So doing that, so again, if you want to know details about how to do that, let me know and I'll be happy to go over that. But evaluating this, we see this cross product, this determinant of this 3 by 3 matrix comes out to be 3 minus 1 times our u of x minus a -12 minus 0 times our u of y plus 4 minus 0 times our u of z. And of course we can simplify that. We can take all those together and we can say that this is then ultimately equal to 2 in our x direction plus 12 in our y direction plus 4 in our z direction. And so this would be the answer for our first part here. There is a different way to do this using cross product properties. Personally, I think it's a little more convoluted and confusing, but if you're interested in seeing that, take a look at page 18 in the textbook, and that shows you how to do that. Okay, so that's our first part. let's move on to our second part here. All right, so let's copy this and let's come down here. Let's go ahead and start on a new page. All right, so now we want Q dot R cross P. So the first question is, what operation are we going to do first? So what operation is first? So take a minute to think about that. Maybe pause the video, try to work it out a little bit. So are we going to do this dot product right here, Q dot R first, or are we going to do R cross P? So unlike the previous part, we don't have any parentheses to indicate which one we should do first. Well, if we think about it, there's only one right way that we can do this, and that's to do our cross product first. And the reason is that if we were to do our Q dot R first, that's going to result in a scalar value. And of course, we can't have a scalar crossed with a vector. So in this case, we have to have our R cross P occurring first. Okay, so since we know that we want Q dot the quantity of R cross P, we can now write that out. So our Q vector, we had a 2 in the x direction, -1 in our y, and 2 in the z. Again, angled brackets because this is a vector. And we're going to dot this with our cross product of those two vectors R and P. So again, it's going to be a 3 by 3 determinant, ux, uy, uz in our first row. And then R is going to be our second row, so that had a 2 for the x component, -3 for the y component, 1 for the z component. And then in our third row, we have our P, which is 2 in x, 0 in y, and -1 in z. All right, so let's go ahead and take that determinant. So we have our Q, which is still out front, just waiting to do that dot product. So that's going to be dot with, and now we're going to have 3 minus 0 times u of x minus a -2 minus 2 times u of y plus a 0 minus a -6 times u of z. Okay, so let's go ahead and simplify that a little bit. So we've got our Q, 2, -1, 2, dot with, so we have 3, 4, and 6 for our second vector there. So of course now for dot product, remember what we do for dot product is we're going to take the product of our x components, we're going to add that to the product of our y components, and add that to the product of our z components. So what that looks like is we're going to have 2 times 3 plus -1 times 4 plus 2 times 6. And so putting all of that together, we see that equals 14. So that would be our answer for the second part. One thing we can notice too, though, is that this form is the same as what we saw when we used our scalar triple product. So instead of doing what we did and doing a cross product and a dot product, we could have used our equation for the scalar triple product. And so what that looks like is we have Q dot R cross P is equal to a 3 by 3 determinant, but now we put our Q up here in the first row. So we have QX, QY, QZ, and then the second and third rows would be the same as we had above. So RX, RY, RZ, and PX, PY, and PZ. So that would be an alternative way that we could have solved this problem. Maybe a good thing to practice just to see if you're able to do that. One other thing I'll note too, we can of course do these dot product and cross product operations in MATLAB. I believe the operation commands are dot and cross, and then we have our arguments, which of course are going to be vectors in parentheses there. Okay, so the last part for this video we're going to look at is part 3. So let's bring that down here. So for part 3, we see we want to have P dot Q cross R. So let's go to a new page here. Okay, so this looks really similar to what we just did. So we could ask ourselves again, well, what product do we need to do, or what operation do we need to do first, our dot product or a cross product? And from the same reasoning, of course, we can say we need to do that cross product first. But before we do any work, let's think back to our scalar triple product again. So we had sort of two equations for our scalar triple product. One was this one that we already wrote up here. The second one was relating different forms of this, basically our problem statement here for part 3. And so what it said was basically if we have P dot Q cross R, it says that that is equal to Q dot R cross P, which is equal to R dot P dot cross Q. And so this was basically just where we had A, B, and C, but remember I said if our first one we have A, B, C, we just move our A to the end, so then we have B, C, A, and then we move the B to the end, so we have C, A, B, and that's how we sort of went through these. So of course we could kind of assign a P to the A, Q to B, R to C, or if you're good at seeing the patterns, you don't necessarily need to do that, but at any rate, these equalities stand, and we'll notice that the second term here is actually what we just solved for in the previous part. So Q dot R cross P, we already know, so therefore we already know that this P, let me just get this one guy here. So we know this right here is equal to 14 that we found in the previous problem. So of course we could have gone through and we could have done a cross product and a dot product again, but it's advantageous to be able to see these use these relationships as shortcuts to avoid work in certain areas. So that's all for this first video. In the second video, we're going to come back and we're going to look at parts 4 through 6 of this example.